Hello Internet! Today I wanted to take a look at doing some really basic lighting on vertex and fragment shaders in Unity. And the reason is because typically when we've made shaders, we've used the standard surface shaders. And those are great because they come with all the stuff you need in order to get lighting working in your shader. But if you create like a default unlit shader, you're going to get a vertex and fragment shader, and it's going to look like this. So I have pretty much all the basic geometry in this scene here, except they're using the diffuse lighting shader that I've created, which doesn't actually do diffuse lighting. It's just this. And so it looks super simple. It's just doing some basic vertex calculations and then some fragment calculations. I'm not going into those right now because we're going to be getting into those. This is going to be kind of a longer video because I'm going to take this very slow and try to kind of walk through what all of this is doing, and kind of treat it like you've never done this before. So if you have, check out the code in the description, and you'll see the shader we end up creating. Or if you're just curious about how to do diffuse lighting, the answer is dot products. But we'll get to that in a bit. First, I just want to create a new standard, I guess, unlit shader. Because we're doing our own lighting, we can't use Unity's standard shader. That has all of the special stuff that is actually causing it to be lit. So if we click this standard surface shader here, that's not what we want. It actually does different things. So like this standard shader here is going to be giving a type, a shader type. I don't know what this is. This is Unity special stuff. A pragma of surface surf. And so what that's saying is we're going to be using a surface shader, and the function that implements that shader is surf. So down here we should find a surf function, and we do. And so that has some sort of inputs and then some sort of outputs. In this case, it has a special in-out value that it's actually writing to. We don't really care about this, but it's very different than the diffuse shader we were using. There is no surf function here, because that surf function behind the scenes actually gets translated into a whole bunch of extra stuff. So there's actually this show generated code thing here. And you can see, now that we're showing the generated code for that standard shader, there is actually a vertex and a fragment shader. Also, you'll see our 100-line shader is now 1,600 lines. And this isn't code that you need to know what it does. This is extra stuff. This is all of Unity's extra compilation stuff in order to get what you wrote in your surface shader working. Actually, it looks like we've stumbled across our code right here. And so this is in here somewhere. Actually, it's probably in here multiple times, but it's doing all sorts of stuff in order to make that work. And that's for cross-compatibility issues, but also it's what actually stores all the lighting stuff. Like I said, we're doing our own thing. So we're gonna just ditch that standard shader and do a create shader unlit. And I was using diffuse lighting as the name for it. So we're actually going to reuse that name, and it looks like Unity just picks it up. That's great. So this is an unlit shader. And what that means in practical terms is that it's a vertex and fragment shader with no lighting logic in it. And so the way shaders work is there are typically two programs that run in order to accomplish getting the thing onto the screen. The first one is the vertex shader. And so that's defined here. We were kind of looking at these pragmas before. If you see this, it's saying pragmas vertex vert. In this case, that's giving us a function for a vertex shader. So down here, we should have a vert function. And that just needs to match the expected parameters for a vertex function. And you can find those. This one already does that. And we have a frag as well, which is our fragment shader. So the vertex shader is what is actually handling the vertices in your mesh. So if we go back here, This is kind of a poor example now because we have sort of everything in its uncolored state. Let's do wireframe mode. So you can see everything is sort of composed of these points. In this case, it's all composed of lines because these are actually the edges connecting all of the points. What we really care about when we're talking about vertices is each of those individual points, sort of where my cursor is, along these cubes or along these quads or whatever. Those are the vertices we're talking about. And so each of those vertices is going to store some amount of data. It's going to have like a position, like where it is in the world, and a direction about where it's facing. Things like that are all stored in your vertex shader, or are all stored in your vertex data. And your vertex shader can manipulate those and then pass them down further into your program. And so when we're talking about a vertex shader, we're talking about something that is actually working with these vertices. And then when we talk about fragments, that is actually what you see. And so what ends up happening is your code is going to go and do vertex logic. There's actually stuff that happens behind the scenes that we don't really need to worry about because we're in a game engine, and game engines handle some of the stuff for you. In this case, what ends up happening is your mesh data gets fed into this. And so we end up with these various meshes. And then from there, that goes into our vertex shader. The vertex shader is what is responsible for getting our mesh, all of these coordinates, into world space. And so what we effectively have, like I have 3 cubes on this right-hand side over here. Each of those cubes have the same vertex data. They all have all of their points in the same spot. They're not 3 different meshes, they're the same mesh. But they're in 3 different spots in our world. The shader is what is actually getting those into 3 different spots. And we can actually look at the specific part right here. So we have a few things that happen in this vert function. What ends up happening is we feed in this app data, which is some amount of extra information, and then we feed out this v2f, which is just the output from our vertex function that is fed into our fragment function. And so what we end up doing is doing this with our vertex, which is doing the UnityObjectToClipPos, which is translating this vertex into something that we can actually use inside of our mesh. So the vertex here, the v.vertex in this app data, is the position of the vertex in the mesh, in the object. And so all of those for those 3 cubes should be the same. The difference is what is actually lying inside of this function, which is actually doing some matrix multiplication that we're not going to get into. Matrices are magic. And I think that's probably the best place to leave that for now. But a lot of what actually makes vertex shaders work is matrix multiplication. And so that's sort of what's doing that there. And that ends up translating it through a few different positions in order to get it into a space that we can actually use everywhere else. And so once we've done that, we do a few more things. This is translating the UV texture into some coordinate space that's more useful. And then it does some Unity fog calculations. If you don't want fog, you can just delete that. And then the fragment shader is going to actually receive that. But whereas the vertex shader gets called for every vertex, the fragment shader is going to get called for every fragment. And so we talk about fragments when we're talking about shaders because they're a little bit different than pixels, but you can kind of think of them like the same thing. So effectively, your screen is divided into pixels, into individual dots that you see. You can think of those like a fragment, like a virtual pixel, and it's sort of a representation in shader space of what that is. And so when we're looking at vert or fragments, they're a little bit different than pixels because you can actually have multiple of them in one spot. So whereas a pixel is like what you would see, if I were to go over here, there are multiple meshes overlapping and multiple fragments because of that overlapping in the same pixel. And so that's just sort of why they're differentiated. But you can, for the most part, think of them in the same sense. They're doing more or less the same thing. And so a vertex shader gives you a little bit more generic solutions to things. It lets you modify the vertices, for example, but it doesn't affect what's actually like drawn. It tells it where things are. It will tell Unity my mesh goes here, but the fragment shader is what is actually going to determine what color to make the thing. And so that's sort of where all the magic happens. Right now, where everything's white because all we're doing is just pulling out the main texture and setting that to the color with some fog. And our main texture happens to default to the white. So we have these properties up here. These properties, this properties block, is Unity specific. It's not a shader thing or anything. This is telling Unity what properties exist for your shader so that it can create an inspector for you. So when you go into your material, we can see our texture and get the main texture. And if I want to, we can just swap in like a rainbow or something. And now all of those have an unlit rainbow texture on them. And there we go. And so that's sort of what the default is going to do for you, but it's not really what we want. What we're trying to do is get it lit. And so when I talk about diffuse lighting, it's more lighting like a soft object. And so when you think of like metal, for example, you're lighting a very reflective surface, whereas a diffuse surface would be very matte, like a fabric or something. And so light kind of hits it, and then based off of the angle of the light, it is more or less lit. And there's no like shiny spots or anything special like that. So effectively, we want to point some sort of light at it, and then light up the spot that is directly facing that light the most, and everything else less so. And that's pretty much what we're trying to do here. Have I covered everything else? I think so. I think we've done most of the basic stuff. The only other thing I should call out is this main texture here. It exists in two spots. There's a main texture there, and that needs to also exist down here. For textures, there's actually a second thing that can exist in order to store text or UV coordinates or UV information, and that goes in here. But for the most part, if you add a property, you should also add some sort of field in order to store that. Otherwise, it's not gonna work, and you're just not. Yeah, it's just not gonna work for you. So what we need to do is figure out how to actually make this thing work. So we're gonna kind of step through and look at sort of what we have right now. And honestly, none of this is actually going to be super useful as it is right now. But we can actually turn a lot of this into useful information. So I think the best place to start is let's inject this vertex, the vertex from our mesh data, not from the world space. Let's inject that into our fragment shader and draw that. Just so what we should see is that all three of those cubes should have a similar result. Whereas if we use the output vertex, we should get different results. Well, I guess we can start with the output vertex just to show that it is different. And we can just do i.vertex, something like that. And so this is just swapping out that texture lookup with the vertex information, which should give us coordinates. And it's all yellow, which should mean, actually, now that I think about that, that should all be yellow. And what ends up happening is we have X and Y space on our screen, and in that case they were all greater than or equal to 1, and that makes total sense. So that explains why that doesn't work. If we were to divide that by something useful, let's say 5,000, we might get something a little bit, more useful, and we'll kind of get this red in the bottom right, green. Okay, that's a little bit too ambitious. There we go. 2,000, sure. All right. And so what you'll see looking at this is we have green sort of in the top left, we have red in the bottom right, and then as we move into the top right, we get more of that yellow, which is sort of a combination of the green and red. And so this is sort of the coordinate space that our vertex shader ended up moving everything into. And so it's sort of the camera space. It's sort of what the camera can see. The cool thing is it's actually screen space more or less, which means that we actually kind of have a good idea of where things are on the screen from this result, which is sort of why it's used for clipping, because you should have a general idea of where things are based off of that result. And you actually know if you need to draw things or not, because if the vertices or vertices are outside of that screen space, so if like you get a negative value for whatever reason, that's either off to the left or below the screen, and neither of those need to be drawn. So that gives you a sort of handy way to do like super basic optimizations. But we're not getting into that. That's a totally different thing. So we have that. Let's inject a float for original vertex. We probably don't need that. That should be fine. That might not be fine. We're going to try it anyway. So you'll see there's labels on all of this stuff. That's used to kind of signify what these specific things are in your code. You can kind of fudge them, and it sort of works. For the most part, you can just use more of the texture coordinate things. So if I really wanted, I could just do text coord 1, and that should work too. But it should be fine. Famous last words. If I leave that blank, it might not be fine. So we need to make sure our vertex shader sets every output value before passing it back. And so somewhere in here, we just need to do o.originalVertex equals v.vertex. And so that's just going to save that original vertex value into this. And one of the interesting things you may be seeing when we do this is that we don't just get, like for our cubes, there's 8 vertices, 4 and then 4. The interesting thing is we're actually not going to get just 4 colors. We're going to get a whole number of colors. That didn't work at all. What did I do wrong? Shader is not supported on this GPU. What have I... Oh, okay. Fun. Let's actually just add that back. There we go. Is it happy with me now? No. We may not want to do this. What have I done? That should work. Huh. Okay. Well, lesson learned. Don't improvise on the spot. So what we should have seen, and I guess, can we still fake it? We can probably still fake it. What if I... This is a really bad idea. v.vertex. That's not going to work. That's really not going to work, is it? We're going to try. I mean, why not? That's sort of what this channel is about, right? Exploring and breaking things. Usually I'm the one doing the breaking, but I imagine that's going to cause all kinds of issues. This should cause all kinds of issues if this works the way that I think it works. Yeah. Perfect. Okay. Good. I think that's what I wanted. Actually, I have another hypothesis. I'm gonna test just quickly. I don't think it's this. This doesn't seem like it should be the problem. So there's multiple of these texture coordinate things of these labels, and we should be able to just increment that value and it should work. That shouldn't be the problem, but I think it doesn't like it when I do this. And so what we're going to try instead is to kind of clone it. And this is, I think, probably the worst way to do that. But we're going to do it this way. .w it's a vector 4, so there's actually X, Y, Z, and then W, because that's just the next letter that made sense. And so there's 4 values, get our original vertex. That should just copy it. And I think we should be fine. The fragment shader should be working. But we're not getting any sort of useful information. It's just that it isn't supported. Exclude renders. Oh, there we go. So Unity has this tendency to inject things into your code. So I deleted it, but we had this pragma called exclude renders direct3d 11, and they actually had placed this in here that actually pointed us towards where we have or where we wanted to look. So struct v2f members original vertex, which was referring to this because we didn't have a semantic label on it, but we've added that now, so that can go away. There we go. That explains so much. That makes a lot more sense. But this is sort of what I wanted to get to. And it's kind of gives you a little bit more information about like how these meshes work. But you can see that all these cubes, they're in a bunch of different orientations, but they all have a green side, a yellow side, a red side, a blue side, a cyan side, a fuchsia side. All of them have the same information. They're just all rotated. But the interesting thing is we didn't get 8 values like I was talking about. We didn't get 1 per vertex. We actually got 1 per fragment. And so we didn't do any math to interpolate those. There's nothing here to blend those values. What's actually happening is in your graphics program, in your shader stuff, once your output from your vertex comes back, what ends up happening before your fragment shader gets it is there's an interpolation between the two. So each of these points, each of these vertices, is actually interpolated between. And so if we have, like in this case, 1 and 0 for whatever value, like red it looks like, when we have 1 and 0, what ends up happening is between 0 and 1, we end up with all the values in between as we move between them. And so that's actually a really handy tool for us because it means that we can use really basic shapes and get really complicated things. And so this actually gives us a really powerful way to kind of interpolate between everything that we have in these meshes. And we're going to take advantage of that in order to get our lighting to look better. Because there's really 2 ways we could approach doing this lighting. We could calculate the lighting value in our vertices, or we could calculate it in the fragment. And so those are sort of the 2 options for this. If we do it in the vertex shader, the problem we could have is if we put our light too close to, we're using a directional light for this, so this actually doesn't really apply. But if we were doing something like a spotlight, for example, and we wanted to put it in the middle of like a wall, there would need to be a vertex there in order to see that. And then the light circle wouldn't be a circle because it would be determined by the vertices that were receiving that light at that position, which probably wouldn't look the best. And so one of the things you can do is kind of put some metadata into each of those vertices and then do the more complicated calculation based off of that metadata at each of the fragments. And so that's actually what we're going to be doing. And so I think the thing is, I've been talking for 20 minutes now, and the solution is actually really easy, but hopefully all of this stuff is kind of helpful and kind of helps make shaders less intimidating. I can remove this now. we don't need that. It was all because I got clever and decided to remove the semantic label. There we go. Everything's still the same. Cool. Great. So what we actually want out of this whole thing is some sort of normal value. We don't really care about the original vertex. That was just for demonstration that it's all actually being manipulated inside of the vertex shader, just so you don't have to take my word for it. Let's add a world normal. And so I'm kind of referencing some of Unity's docs because I forget the name of the functions for these. And we also need a normal input. So each of the values each of the vertices of our, let me see, shaded wireframe? Sure, it doesn't like that. Original vertex is missing, that's why. It doesn't like the fact that we have, or every single one of, what the heck? There we go. That's wrong, but that's fine. Every single one of these vertices has a direction associated with it. It's called the normal. And so like if we're talking about this quad here, that quad, why can't I, there we go. This quad sort of has a direction attached to it. You can kind of see, like, we can move it back and forth. That gizmo there kind of gives you an example of like how the plane whole thing works. But really that applies everywhere, even on something that looks round-ish. It's actually not. I mean, it's all just a bunch of connected lines. But it appears round when you actually look at it, and that's because those normal values can be interpolated between. And so that the interpolation we're seeing here, we can actually apply to those normal values. So the angles of each of those things can be actually interpolated between on the GPU. So we can actually just take those normal values and output them in our shader, like I kind of wrote here. And then instead of looking at the actual vertices, we can look at the normal, which is the direction of that according to the mesh. And so the first thing we're going to start with is get the normal out. So v.normal. This should work. It's not the world normal, but you'll see it's probably easier for I've rotated both of these, so it's probably easier for everything else. But you'll see the top is green. Red, green, blue is the three color or three float values. So X, Y, and Z map to those. So red is along the X axis, green is the Y axis, and blue, which should be on the back here, is our Z. And so you can actually see all of them match except the two rotated ones. And that's because that all this is doing is showing the normals assigned to each of those vertices. And you'll notice a few different things. So these cubes, I said they were 8. I'm pretty sure they're not. There's 4 per face. And that's why they're not interpolated between on the other sides. Same with the top of this cylinder here. There's no interpolation happening between those, but there is for like the capsule or the sphere. And so the handy thing here is we actually get like smooth values. Even though these could be very large, we should still get smooth values because they'll still be interpolated between for the vertices. And so that is sort of how that whole thing is going to end up working. We just need to take this normal and translate it from the current space we have into world space. And so there's a function called UnityObjectToWorldNormal, which does a whole bunch of fun math and converts this normal. The math is going to be matrix multiplication again, but it's going to convert this normal for our mesh into world space for us, which means we'll get a compile error. What? Okay, got it. So this world normal here should be a float 3 because we're actually getting X, Y, and Z. The W doesn't make so much sense for the normal anymore, which means this needs to not be that. It can be a fixed. I haven't really talked about this. I'm using fixed 4 here because that's just what's there. There's 3 different floating point values. There's fixed, float, and half. Not necessarily in that particular order, but all 3 of these represent different floating point precision levels. So that on different graphics cards, they may have a different amount of bits associated with them. And so you can just pick and choose, but they can be used interchangeably. So, or for the most part, they can be used interchangeably. I haven't run into any issues with using them in a mixed fashion, but we're using fixed, so we'll just stick to that. Anyway, what this is doing is assigning X, Y, and Z from our world normal to x, y, and z inside of this new fixed 4-dimensional vector, and then assigning the final version to just have a value of 0. And so that should keep everything good. We actually probably want that to be a 1, because in this case, that W is actually our alpha. So red, green, blue, and then the alpha transparency. That shouldn't matter here, but we're going to assign it anyway. And you'll notice something's changed. We can now rotate these, and the green stays on top. This is actually useful for a whole bunch of things. I've used this for like dynamic snow on top of mountains, for example. It works really well for that. But in this case, what we've effectively done is gotten that normal that was originally only for anything that hadn't been rotated, since it was in object space. Now it's in world space, which means no matter how many manipulations we do to this, or whatever we do to any of these meshes, that normal value should be the same regardless. And so we're getting really close to actually being able to do what we wanted to do in the first place. So we want to create a color, or we want to create light. And so what we want for that is some sort of source. In this case, we're doing directed light. So a directional light. Directional light. Or do we want a point light? We could do a point light. I think we could do a point light. Why wouldn't we be able to? Should we do... Okay, we're going to do a light point. Just because I'm making things up and it just makes sense. So light point position, I guess. And this will be a vector. So that's going to be a 4-dimensional thing. Sure. And we'll just set it to 0 for now. That should be fine. What we're going to do is calculate a vector of the difference between we got the vertex here, which is going to be the world space. That's not the world space vertex. We're going to need a world space here. So what we need is some way to compare that new vector we just created, that new light point, with the position of our object in world space. We don't have that, so we're going to do a world position at texture coordinate 2. There's a few of those, so we should just be able to burn through a few. And I had mentioned that we need to map this value into some sort of value down here. So in this case, we're going to do a float for of light point, and that just creates the field that Unity can assign from this property. And that should be good. And so now we just need to actually get this world position. And I don't know how to do that because I didn't look this up. So we're going to do world position equals Unity object to world pose. I'm guessing here, but I think that sounds about right. This might not work. Nope. Unity to world pose, that doesn't sound right either. So I will go look this up quick because I don't remember the name of the function, and I will call that out. But what we effectively want to do is transform our object space vertex back into world space so we can actually use it. So one sec. Found the name of the matrix that we need. It's the Unity object to world matrix. And so you just use a multiplication function to multiply that matrix by our vertex. We're getting into that matrix multiplication stuff again. We've covered this in the past, and I'm kind of trying to skate around it because that's a very deep topic that I don't really want to spend too much time into because we just can't really answer all of that right now. But what this should do is take our object vertex and translate it into world space for us. And so the output of this function should be a world space position of our object, which means instead of drawing this world normal, we should be able to draw the world position, which I believe I have set up as a 3D vector, so we should be fine. We're gonna find out. There we go. And so now instead of getting normals, we can rotate these and we get more interesting results. And now the values are actually showing the world space position. So our quad actually has color on it again. That's great. And everything gets darker as it gets further down because it goes to 0. And actually these are, many of them are negative off to the left over here. And that's fine. But this at least shows that it's working. So we have a world position. Now what we need is to compare that light point. And so what I want to do is get a fixed 4 of our light direction. Let's do a fixed 3. Light direction. And so this is actually going to be light difference. That's a much better term. We're going to do the difference between our input world position and the light point. So minus the light point dot xyz. So in shaders, there's this really handy thing called the swizzle operator, which is what I just used here. Effectively, there are different values attached to your vertices or attached to your vectors. And you can actually reference them in different ways to get different results. So we used XYZ here to pull the X, Y, and Z coordinates out in that order and turn that into a 3-dimensional vector. But we can actually do like XY, and that will work as well. Or we can do like YZ to create a 2D vector that has Y in the first part of the vector and Z in the second half. And so we can do things like that to kind of mess with it. RGB is also supported, and even RGBA, and W works as well. So like XYZW is perfectly fine. And you can see it used actually in the texture lookup as U and V. But for this, XYZ should be fine. And so that's just going to make sure that we stay in 3D space instead of mixing a 4D vector and a 3D vector. Talking about a lot of math, but there we go. So that gets us a light difference. We're not actually drawing that though, so we don't really, we don't get any value out of that. What we should be able to do is plug this light difference in, and we shouldn't see any changes. We don't. But now we should be able to create changes by moving the light position. So as I move this up, we'll see everything gets darker and darker because we're actually shifting the light up, which is subtracting more from everything else. And so we should be able to just make this whole thing black by just shifting it off into that general direction, off into this coordinate of somewhere. It doesn't really matter. And then if we go the opposite direction by making them all negative, everything will become white. And so that's just giving us a way to kind of diff, I guess, the light position. Now we don't really care about the magnitude of this difference. What we actually want is the fixed 3 of the light normal direction equals a normalize. That's not how you do that. Is that how you do that? We're going to find out. Light difference. Okay. I don't know if this actually works. I don't know the name of the function for this. So light direction, if we plug that in, we should now get a direction towards where the light is as our new vector, which shouldn't change anything, but it should prevent them from becoming too big. And in this case, we actually get vectors out. I don't know the best way to show this other than like down here, where we can, as it moves towards a point, we'll actually get this radial pattern because effectively that's really close. That point right there is really close to where the actual light emission point is. And so what that's going to end up resulting in is some sort of normalized vector, which means it has a length of 1 that we're getting back out of it, and the normals on our mesh should also have a length of 1. And so what we can actually do is take a dot product of those. And so a dot product returns the cosine of the angle between any dimension of vector, which makes it really, really handy for like 3D stuff, because trying to like manually figure out how to calculate the cosine for a like 3-dimensional or 4-dimensional object is not easy, but this actually makes it possible. And so if we give it two normalized vectors, the result is going to be 1 if those two vectors are in the exact same direction. It's going to be -1 if they're like anti-parallel to one another. So one is going straight in one direction and one is going the opposite direction. If they're perpendicular, you're going to get 0. And then it's going to interpolate between those values as you move around. And so what we can do is use that dot product to create this diffuse light. And so if the normal and the light direction are in opposite directions, that is, the material face is facing the light directly, we want that to be equal to 1. So we can actually do a float. Let's do it fixed. Fixed intensity, I guess we can call it. And that's going to be 1 minus the dot product of our light direction and our input normal. And so I did 1 minus because I said if they were parallel, then they would be equal to 1. We actually don't want that because if they're parallel, then that means that the light is facing in the direction of the material. And so effectively it would be the wrong direction. So we're inverting that by doing 1 minus that, which I don't think is correct actually. -1 times that should invert it. There we go. And so that will get us the intensity of the light, which means it will be 1 if the surface is facing the light, and then it will fade to 0 as they're perpendicular, and then it will go to 0. And so we should be able to go back to our main texture now. Or I guess we can do this a little bit more incrementally and just do the intensity with a 0 and 0 as the two other options. And so this should draw a red value for the intensity of the light at each of those positions. Or we'll get a error. The name of this is world normal. There we go. Cool, that's fixed. And now we should see red. And what you can kind of see already is that our light is somewhere in the center there inside of that capsule, which means it is entirely dark because the light is coming from inside and all of the faces are facing away. So all of those values for the dot product should be negative in some way. But then everything facing it actually does get that value. And so as we move this around, we'll get a better lighting result. And so we can just move this in any direction we want. And we'll sort of get like cheap diffuse lighting. It's not going to be perfect, and it's not going to cover every lighting scenario you would want. Effectively, we've created the ability to draw light at a single point, which is fine if you want like really basic or just like simple lights. But for a lot of more complex things, this isn't probably going to cut it. That's why the standard shader is there. But there's certain things that can't use a standard shader. So geometry shaders, for example, which are shaders which add a third function to the vertex and fragment shader that actually allow you to split up your vertex into a bunch of other things. So you can effectively take all these triangles for like this cube and create something extra out of them. We've used that to turn each of them into each of the points of a mesh into like a blade of grass, for example. But yeah, so that is how we get lighting. In order to finish this off, we can actually multiply this intensity by our texture lookup now, which means we'll actually be able to retexture our objects and everything should be good. So now we have that rainbow pattern back because we're using that. But we get lighting. So instead of just being that solid pattern, we actually have some sort of light on it. And you can tweak these values to whatever you want. maybe you don't actually want it to be black when there's no light on it, you can add something to fix that, or you can modify this a little bit and do like 0.5 and just add 0.5 onto the end, which should mean, because this dot product has a range between 1 and -1, we've reduced that range down to 0.5 to -0.5 and then added 0.5. So effectively the range now of this whole function is 0 to 1. And that means that even the backsides should be lit very bright, or very minimally. The only difference might be this capsule, which still does have light now, but it's still very dark. So you can kind of play with this and get whatever you want. But I hope that this is kind of like a good introduction to a lot of like shader stuff, because I don't know. And I'm sure there's other questions and things that I didn't cover. But I kind of wanted to just take a look at this as sort of a way to introduce a lot of those. So hopefully it got at least somebody interested in this. If there's questions, leave a comment or let me know, or join our Discord and we can chat. But yeah, I think that's it. This shader will be out on GitHub, so you can go and grab it. And I think that's it. So yeah, thanks for tuning in, and until next time, see you, Internet.